Good morning, everybody. Okay, welcome to this new section. Sorry if we are late 15 minutes, but this is Spanish time. We are perfect time, actually. Okay, let's introduce, it's a pleasure to introduce Professor Elena Berdysheva from University of Cape Town, South Africa. And she's going to speak about the metric approximation of set-valued functions on bounded variation by integer operators. Please.
Thank you very much, and thank you, the organizers, for inviting me here. I am an outsider also in terms of community, also in terms of the topic, as you will see. Well, I will try to do my best to explain what one of the areas I'm working in. So it will be a long introduction about the situation and, I don't know, some short path with theorems. This is, let me see. This is joint work with a group from Tel Aviv, Elsa Varhe. Okay, we are going to, let me return back, metric approximation of set-valued functions. So I'm going to explain you first what set-valued functions are, in particular set up what we consider and what metric approximation is. So I denote by this capital T over D, the collection of compact non-empty subsets over D. And we consider following setup, set-valued functions for us, which I will frequently shorten like this, or they also live in mathematics under the name multifunctions, or functions that build a compact interval of the real life on the real line into this set. So the argument is a real number and the value is a compact non-empty set. They have plenty of applications in mathematics. I will not go into details because of lack of time. So there is some selection, dynamical system, control theory, game theory, differential inclusions, mathematical economics, optimization. Let me stop here for a moment. These are traditional areas. These are areas where in the absolute majority of cases, the sets, our values, the sets were in addition convex. So there is a big established theory how to work with functions whose values are convex sets. And of course, convex sets are special. We have plenty of methods to work with them, like support functions, whatever. Now, this last thing coming here, geometric modeling, this is a quite modern, quite new thing. It, of course, became now very popular in connection with, digitalization everywhere. And then you can forget about convexity, because what we want to model some geometric objects, and why should they be convex? And here is here is a picture, is an example. I copied that from a PhD student of Shay Kals, who was also a student of Nira and Elsa. So this is this problem what he, for example, considered one of the problems, that we have some three-dimensional object and what's given is the collection of cross-sections. And then you need to recover the object from the cross-sections. One practical application would be in medical imaging. Okay? So I always say that, for example, here are two bones and some device, I don't know, let's say X-ray makes you cross-sections, but the doctor wants to see a three-dimensional object on the screen. So, and forget about convexity, it's not convex anymore. And here particularly, I'm not going to get into details, but this is some piecewise linear reconstruction and this smooth reconstruction, so there are methods. The point is that at least when we go into geometric modeling, we can forget about convexity. As I told you, convex functions are quite well studied, many work. So approximation theory, so in addition to the set-valued analysis, of course, the approximation theory also develops, and here's some selection. I don't say it's full. Richard Whittle in 1979, he adopted a classical Bernstein operator, which is an absolutely well-known, best-studied, well-understood operator in approximation theory for approximation of continuous real functions to this setup to approximate functions, set-valued functions with convex images. So I come from classical approximation theory. So to say, for me, it's something that you learn at school, yeah, at kindergarten, let's say. But I will give you formula later. It will appear later. So just some very classical operated in Nirodin, Elsa Forge, and many students work since 80s, completely different approaches, different things. Michele Campiti, my good friend from Italy, Kropotkin type theorems. Then there is a survey by Murishan, and then one paper also, Babenko, Polishuk, some kind of trigonometric approximation. The usual problem is convexification. This means that if we apply our approximating process, then it converges. Yeah? Well, we want that it converges, but the limit is a function with convex images. So, for example, in this paper by Vitali, his construction, he shows that this sequence of Bernstein operators converges to the convex hull of the given function. So the result is always convex. And of course, it's great if your function was originally with convex images, you solve the problems, but for us, it's not what we want to have. Okay, pioneering work on approximation of set-valued functions with general, not necessarily convex images, V. Arnstein, piecewise linear approximations based on something what we later started to call metric pairs. I will immediately introduce them. So that also already has some age here, as you see, but the idea comes back to him. So what are metric pairs? I consider RD, RD, all norms on RD are equivalent, as we know, so we just grab one norm, doesn't matter which, and then I can, for a point in the set, I can introduce the distance in the usual way. Yes, so this is the closest point. Remember, my sets are convex. My sets are compact. So I always have the closest point. Here I have these two sets A and B, and here is A, and this is this is just the Euclidean norm. This is the distance between A and B. This is the point B here. This is the distance between B and A, and so on. Right? And then the set of metric pairs of two sets A and B is the set of pairs, A in one set and B in the second set, such that E is a projection, so exactly this closest point, or B is a projection of on the other side. Of course, depending on the norm, it can be a unique point. It must not be, yeah? So think about L infinity, then it can be really a continuum of points, their projections. So say if I have the situation that one point exactly realizes the distance, that this is a metric pair. This metric pair is special. This gives me exactly the Hausdorff distance. Okay, I know my problem is I can talk, but I need to put my talk in the frames. That's why I didn't give you here to see standard definition or one of the standard definitions of the Hausdorff metric, but this is an equivalent definition, so we just look at all metric pairs, look at the distance between them, and take the maximum. This is a Hausdorff distance. My set K over D, the set of compact, non-empty subsets over D, together with the Hausdorff metric, is the complete metric space. Okay, and the idea of Arnstein was to create a linear interpolant by connecting metric pairs by pieces of linear functions. Let me make it maybe a small picture to understand, to let you understand how non-trivial it is. So imagine these are two cross sections, and I want to, so these are two sets, I'm trying to do a three-dimensional picture. Now, how do you create linear interpolant? Yes, so clearly you take one point from the below, one point from the up, and connect them by a straight line. But what is the corresponding line? What is the corresponding point? And answer is take a metric pair. So it would be something like this. Okay, let me check the time. The standard tools to work with sets, which is very good for convex sets again, or Minkowski linear combinations. So if I have sets and if I have scalars, then I just consider all possible linear combinations. This is the Minkowski linear combination. It has this property of convexification, and to show you how bad it is if the sets are not convex. For convex sets, it's perfect, just really perfect. Let's see, I take a set A, which consists of 2.0 and 1. Yeah, so now my codomain is now K of R, compact subsets of R, yeah? 0, 1, and then I take an average of n copies. Yeah? So if you take an average, you want to see exactly the set, right? An average of n copies of the same set, I would expect I get the same set. Look what happens here. So these are 5 copies, this is the result. So it's not, of course, it's not literally a convex set, but you see what happens. Fills the gaps. Doesn't work. Yeah, so Minkowski linear combinations don't work. What is a substitute? So there was a tool developed by Nirav, Elzo, and Elena exactly right before the time I joined the team. And first I need to introduce some intermediate step. This is what we call metric chain if I have sets. So here, for example, on this picture, I have these 4 sets for intervals. Then I go over points such that 2 neighboring points are always a metric pair. So here, these red lines, they show some metric chains. So for example, this is a metric chain. This is a metric chain. Here is the straight line is a metric chain, and so on. Okay, this CH is chain here, it's the collection of all matrix chains. And now the metric linear combination, how it comes. So exactly, I have sets, I have scalars, and I consider again linear combinations of elements, but now the elements which I take here belong to one metric chain. So it's of course a subset of the Minkowski linear combination, yeah, but the point is that we take much less points, much less combinations. And look at my example, now it works. So this was exactly my example. Each set consists of 2.0 and 1. I have only 2 metric chains here, only 2 matrix chains. Why? Because if I am at 1 and I look at the closest element in the next set, I will never be able to go to 0. I always stay at 1. And if I am at 0, then I'm always at 0. I never will be able to jump to 1. And now when I take the average, it's exactly this. Yes, so once again, I have here only 2 metric chains. So it looks appropriate. Okay, there is one point. However, the metric linear combination depends on the order of the sets, yeah? Because I always look at the next, yeah? So I need to look at the metric pair, the next set. In general, is of course the restriction not for us because we're going to approximate functions. Yeah? So we have some natural order of these cross sections. Integral, okay, there is developed integral for set-valued functions, again with convex images. It's the Oman integral. If I have a set-valued function, a single-valued function S is called a selection. So S of X is always an element of F of X. So if I have a graph of a function, yes, so here is a graph, this is A, this is B, the value at each point is an interval, yes, so any single-valued function like this is a selection. Yes, so this is an example of a selection. The Oman integral is the volume take all integrable selections, take all integrals. It gives you a set. This set is called the Oman integral. It's of course convex, so it's a well-known fact that the Oman integral is always convex and compact, even if the values of f are not. Again, a modification of my example. Now, I took a function which is constant function. The value is always 0, 1. This is the graph of this function. On the interval 0, 1, let's look at its average. Here we have a really convex answer. The average is the entire interval 0, 1. Why? I just take point alpha between 0, 1. I have this red is the corresponding selection. Yeah, it's an integrable selection. The integral is exactly alpha. Yeah, so it gives me all possible points here. So it really filled the gap. Yeah? It's perfect. As long as you stay in the world of convex values, it's all perfect. Yeah? If you go away from convexity, it's a disaster. All right, this is why I'm telling you. Useless for work with set-valued functions with general, not necessarily convex images. Let me check the time. Okay, metric selection. So now we gain the same ideas for metric combinations. We are going to do the same for the integral, but we take much less selections in the integral so that it stops filling the gaps. Again, an intermediate step. So now you can read it, but let me better explain it. The chain function. So now I have some metric. I have a partition of the interval, and then I have some metric chain, and then this is just the piecewise constant function. So something like this. So I have a selection, I have a point, let's say start here, this would be the closest point. Okay. Of course, it can go out of the graph, it's not necessarily a selection. Yeah? Okay, now a selection is called a metric selection if it's a pointwise limit of a sequence of chain functions, such type, when the size of the partition goes to 0. And these are the right selections. We denote the set of all metric selections by this S of F. This is an example here. The red lines are selections. Metric selections are lazy selections. So you can think about it because it always looks for the closest point next to you. If there is a chance for it not to change the value, it will not change the value. So if the graph stays in the interior, if the point stays in the interior of the graph, then it's always constant. Like for example, this one, it went here, it arrived at the point it cannot continue with the same value anymore. Now it has a choice, go up or down. I pick this one, goes, and here it continues. It doesn't need to change anymore. So lazy selections. Now the class I'm going to consider, I'm going to work with, I will denote it by this capital F, is the class of set-valued functions of bounded variation with closed graphs. The variation is taken in the metric space with the Hausdorff distance. Good, closed graphs are quite usual assumption in this theory. Good news, every point has a metric selection, so there is a metric selection through every point, and the graph of the function can be understood as a collection of metric selections. So always think about it. You saw maybe in your computer science department, you know, thick cable, and if they cut it, then there are many thin cables coming out of it. Yes, so this how we think of a graph of a set-valued function. So imagine many individual functions put together in this big graph. Nice property, it's closed under pointwise limits. A pointwise limit of metric selections is a metric selection. And this is maybe the most important thing for the analysis. Regularity of metric selections. For metric selection S in this class, we always have that the variation of the metric selection is bounded above by the variation of the function. Let me explain that this is something you cannot expect in general. Okay, let me repeat this graph. So look, this is the graph of the function. Lazy selection will stay, don't change here. So this is my lazy selection. You see it's controlled by the graph. Now let's see that it doesn't work for any selection. Yeah, any selection can really unbounded variation. Or at least, well, what I'm trying to say, not well, in this picture it can. In general, there is no bound possible. Look, I can have a selection like this. And so on, yeah? You see, I can make a variation as big as I want. Yeah? So this is exactly the point. Okay, not just the property of the variation is inherited, all suitable properties, all suitable structural properties are inherited. So here I didn't want to bother you with a long set of different formulas, but let's think about moduli of continuity, whatever, some suitable, depending on the functions of bounded variation. So they are not continuous, but they have limits, of course, and right, left limits at that point. So we can have one-sided, local, whatever, quasi. So it's all controlled by the mother function, the big function. Not for just selections. Just selections can be anything. Okay, now the metric integral is defined in this way. Exactly the same, yeah, we took all possible selections and all possible integrals, but we consider here only metric selections. And of course, it gives you a much smaller set. Back to my example, again, there are just two metric selections, and the average will be exactly the set 01 as we wish. Okay, approaching what I'm going to show you actually in the last minutes, we can put a weight function here. Yeah, so it's convenient that we just not integrate the function, but we integrate the function times some scalar weight function. And now, yeah, now, as I told you, it was going to be a long introduction, and now in the last minutes, just a few words about the actual result I want to show you. Approximation operators, which are integral operators. So I have here a sequence of kernels. This is my function I want to approximate. This is a sequence of operators. And kernels must have some typical normal properties. Roughly speaking, it's localization on the diagonal so that I recover the value. Okay, here are my operators. The Bernstein-Durmeier operator, this is one of those classical positive linear operators in the approximation theory. P and K are Bernstein basis polynomials. This is the kernel. Another good guy, well-known guy, is a Komtarovich operator, where this would be the kernel. Okay? So if I just use it for real functions, it's a very classical approximation theory. But what we do that we adapt them for set-valued functions via this metric integral. Yeah? So now this is a set-valued function, and this here is now a metric integral. Michele Campetti started the same, exactly the same operators, also practically the same time, but based on the Human integral for functions with convex images. It was very interesting to discover, to compare these things. You cannot really compare because there's a different setups, yeah? So you cannot compare in this sense. But it was very interesting for us to see that we were working on the same, but in two different situations. Okay, but what we started with were not that classical approximation operators, positive linear operators. Actually, we started with Fourier series. Yeah, so this was the original work. This is the Dirichlet kernel. So if I now consider this exactly for real-valued periodic functions, 2π periodic functions, and this gives you exactly the nth partial sum of the classical trigonometric Fourier series. So this was our way. Okay, notice, however, that we have a problem here, some small specific feature that even if my set-valued functions was periodic, like here I have two copies, and then this square with the whole is, but it can have selections which are not periodic, because if it started here, it had the whole. Okay, this point is closer, it could, but it will never come up again. So there is some small something special, but otherwise you just can think that this is a straightforward way to carry over Fourier series to set-valued functions. We Googled and Googled and Googled and Googled for hours, and we couldn't find anything. It looks like that the first attempt at all to define trigonometric Fourier series for set-valued functions, we couldn't find anything, not for convex values, nothing, yeah? So it looks like that it was really the first. We couldn't find any traces of any Fourier series on the web. Okay, I have to finish. Here this Tn stays for any of our operators. Well, these three examples, but any of them, and now to see the last thing. So we were able to show the convergence, exactly what you expect if you work in approximation theory. So if X is a point of continuity, then I have convergence of these sequences. So think about it as a nth partial sum of Fourier series in the Hausdorff metric. If f is continuous in a closed interval, then the convergence is uniform. And what happens in the jump? Yeah, functions of bounded variation, they can only have discontinuities of first order. So it's continuous, so we jump. Oh yes, we have also here, we describe the set somehow. So in the original theorem, in the first variant of the theorem, we have it described in terms of metric selections. So it's first description, the only thing is that you don't want to have this. Yeah? You want to have something, a limit described in terms of a function itself. We were not able to obtain it. So you see there's two papers. This is the trigonometric paper. This is the approximation integral operators. We're not able it. And here I just repeated this formula. You know, this is a last thing still submitted is that under some reasonable assumptions on F, we have for the limit exactly what we want to see. It's of course, it's a metric linear combination. Everything is metric. The linear combination is always metric. But this is exactly what you want to see. It's half of the left-sided limit. Linear combination is the half of the right-sided limit. And in case of Fourier, it's exactly the Dirichlet-Jordan theorem. Okay. To get it, let's jump over this. It's not much mathematics here anyway, but let's jump it over. Thank you very much for your attention.
Thank you very much, Elena, for your nice talk. And do you have any questions or remarks?
It's quite interesting. What is about Fourier transform on real line something? Could you give some ideas?
Well, a natural equation, thank you. Yes, right now we have the entire thing on a fixed interval, on a compact interval.
Yes,
so now the next step, well, you see, I mean, I would want to say we are just starting it, but when I saw now preparing 2018, I was scared, yeah? So 6 years, like yesterday. But of course, this is the next thing to think of. So we need some kind of improper interval here to integrate from minus infinity to infinity. This is thing in our mind there.
We are working on integral operators over real line, many operators, not only Fourier. So it could be interesting how you can expand this for.
Well, yes. Well, but I tried to tell you. So if my kernel, if I have an integral operator with a kernel, and if my kernel satisfies certain assumptions, then this entire theory can be run. Yeah, so the assumptions, I didn't put them because it would be a boring long slide, with something.
And also some question about Lebesgue integrable functions. Did you think about Lebesgue integrable function, LP function, some kind of?
No, this is not a Lebesgue integral, this is a Riemann integral.
Yeah.
And the problem is, that's why we work with functions of bounded variation. We work with Riemann integrals. So this integral is conceptually Riemann. But I don't see a straightforward way, so it would be some different construction.
But still TS integral. Still TS integral, for instance, for bounded variation.
There are things to think of. This is why you have students, right? To drop this on students.
Thank you.
Yes, thank you.
So, any other question or remarks?
I have a question about the first part of your talk. Since uniform spaces appeared, a lot of people try to generalize things from metric spaces to uniform spaces. For example, a very well-known example is convexity. The notion of convexity was transported to metric spaces by means of convexity structures and stuff, and then it was also transported to uniform spaces. So my question is, do you know if maybe the first things that you were talking about at the beginning of your talk, like metric projections and stuff, like any of that has been transported to uniform spaces anyhow?
I don't know, thank you for this. I know that this group, exactly, I showed you the names, Babenko, Polishuk, so there are some other people, they work on some, I'm afraid to tell something wrong from my mind, and they work on some more general setup. Yes, so we would be, in our setup, it would be a special case, but I'm a little bit afraid now to talk from my mind. I usually tell, especially to one of my students, who I always make a joke is better mathematician than me, like I'm a simple metric space person, I'm a simple RD person. Yes. But thank you, I have to check. Thank you.
Okay, thank you for the very nice talk.
Thank you.
Okay, any other question? Okay, let me ask you just a curiosity, because you study set value function from the interval to the compact convex sets, no? In RD. But if instead of the compactness, if you require just the imaginers are bounded convex set, because
in RD, yes, of course, in RD, this is exactly it. Yeah, okay. we teach it in real analysis, so beginners.
Yeah, yes. Okay, also distance makes sense also, no? Between two sets, with two bounded sets, you can consider still Hausdorff distance, and then you can do the same thing, no?
Repeat it, please.
No, like when you introduce the projection between two sets, no?
Yes.
You use the Hausdorff distance, no? Okay.
Kind of don't understand, but okay. I ask you later. Okay. Yeah, but well, we are now in a complete metric space.
Okay.
So this is I mean, some kind of the analysis, we do it immediately in an arbitrary complete metric space, because we realize that we don't actually use any specifics of that. So if I...
Okay, in any case, we can...
Yeah, but let's talk after that. Thank you. Yeah.
Okay, if you don't have any other question, let's thanks again the speaker.
Thank you very much.